story, really. How do we tell the real metals from the imposters? So let's start our investigation. You'd think it's pretty simple, right? If it's shiny and strong, hey, it's got to be a metal. But in the world of elements, looks can be, well, really deceiving. The most obvious clues can actually be red herrings designed to throw us completely off the scent. So yeah, our investigation just got a lot more interesting than we thought.
Every good investigation starts with the obvious stuff. So, our first line of inquiry is going to be the physical properties of metals. The things we can literally see and touch. Let's build our initial suspect profile.
Okay, clue number 1, the shine. That classic, unmistakable metallic gleam you see when a surface is polished, that's called luster, and it's probably our most obvious piece of evidence so far.
Next up, malleability. Now, that's really just a fancy way of saying it can be hammered into super thin sheets without shattering. Gold and silver are the absolute champions at this, which is exactly why they've been used for all that intricate art and jewelry for thousands of years. And right alongside that is ductility, the ability to be stretched out into a thin wire. This is what makes all of our electrical wiring possible. But I mean, just how far can we actually push this property? Get ready for this, because it's kind of mind-blowing. A single gram of gold, that's about the weight of a paperclip, can be stretched into a wire 2 kilometers long. That's not just ductile, that's absolutely incredible. So let's round out our profile here. Metals are usually hard. They conduct heat and electricity really well, that's why your cooking pans are metal, and they're sonorous, which just means they make a ringing sound when you hit them, like a bell. So our case seems pretty open and shut, right?
Well, this is the part of the story where our investigation hits a massive wall. It turns out our neat little list of clues has some major exceptions. These are the rule breakers, the elements that are about to blow this whole case wide open. Let's start with the most basic rule we have. Metals are solid. Except, well, mercury. It's 100% a metal, but it's a liquid at room temperature. Right off the bat, our number 1 clue is basically worthless. Okay, what about hardness? Metals are strong, they're tough, right? Not always. The alkali metals, like sodium, are so soft you can literally cut them with a regular knife. So, another clue? Completely debunked. And get this, the deception goes both ways. We assume nonmetals are all dull and boring, but then you've got iodine. It's a nonmetal for sure, but it has that classic shiny metallic look. It's like an imposter, hiding in plain sight. And here it is, the final nail in the coffin for our physical evidence. Conductivity. Nonmetals aren't supposed to conduct electricity, but graphite, which is just a form of carbon, absolutely does. It's a key ingredient in batteries. Our entire case based on physical clues has completely fallen apart. So we've learned a pretty crucial lesson here. We just can't trust appearances. Our initial clues are totally unreliable. Which leads us to the big question. If physical traits are lying to us, what's going to tell us the truth? The answer, my friends, is chemistry. We need to stop focusing on what these elements look like and start investigating how they act. It's time to move on from a simple visual ID to let's call it a chemical test of character. Let's see how these elements behave when we put them under a little pressure. Our first test is actually really simple, but it is incredibly powerful, the water test. We're going to expose different metals to water, but we'll ramp up the intensity. First cold, then hot, and finally steam. This should really reveal their true colors. And the results are, well, they're pretty dramatic. Potassium and sodium are so reactive they practically explode in cold water. Magnesium needs hot water to get it going. Iron and aluminum are a bit tougher. They only react with steam. And then you have gold and copper. They do nothing at all. All of a sudden, we have a clear power ranking emerging. This chemical behavior, this is what gives us something definitive, something our physical clues just couldn't provide. So it's time to reveal the official power ranking of the metals, the reactivity series. And our final piece of evidence is something called a displacement reaction. The rule here is so simple. A more reactive metal will always kick a less reactive one out of its compound. It's like a chemical showdown. If you put an iron nail into a copper sulfate solution, the iron will literally push the copper out of the way, proving it's more reactive. And here it is. By combining all of our chemical test results, we get the reactivity series. You've got the super reactive potassium way up at the top, all the way down to the completely unreactive gold at the bottom. We've cracked the code. This is the true measure of a metal. But why? A good detective always wants to know the motive. What's behind all this behavior?
To understand that, we need to go even deeper, right down to the atomic level. It turns out it's all just a game of electrons.
Here's the secret. Every single element has one ultimate goal in life: to be stable. Just like the noble gases. And to do that, they need a completely full outer shell of electrons. This desire for stability is the driving force behind pretty much all of chemistry.
And this is where we see the fundamental difference. Metals, like sodium, they only have a few electrons in their outer shell. So for them, it's way easier to just give those away. But nonmetals, like chlorine, have an almost full outer shell. They desperately want to take electrons to finish it. So you've got your givers and you've got your takers.
So, what happens when a giver meets a taker? Well, you know what they say, opposites attract. Sodium happily gives its spare electron to chlorine. Sodium becomes a positive ion, chlorine becomes a negative ion, and bam, they stick together like magnets. And the result? Sodium chloride, which you probably just call table salt. This simple little exchange of electrons is the secret behind countless compounds all around us.
So, our investigation is finally complete. We went from misleading physical clues all the way to the definitive chemical code. An element's true identity isn't about how it looks, but about how it plays the game of electrons. And now that you know the rules of the game, what other partnerships can you spot? What givers and takers are at work in the world all around you?